Hello, and welcome to experiment number 4, energy measurements. In this week's experiment, we're going to look at the overall equation of total energy plus work less friction equals total energy. And this will allow us to examine the conservation of energy from the perspective of three different systems. In each system, we will either be looking at the potential energy due to gravity, the kinetic energy of an object, or the potential energy of a spring. In each case, we'll review the formulas as well as the units before moving into the individual parts of the experiment. And so to begin, we are first told that the potential energy due to gravity is equal to the mass times the acceleration due to gravity times the height. And as a review, you should be prepared to use the appropriate units for each substance or each portion of this reaction. Or of this equation. And so we would begin by saying that in the potential energy due to gravity, when using the mass, we are going to use units of kilograms. The acceleration due to gravity will be in units of meters per second squared. And the unit for height will be meters. For kinetic energy, we'll be using the equation 1/2 times the mass times the velocity squared. And again, our mass will be in units of kilograms, and our velocity will have units of meters per second. Finally, when looking at determining the potential energy of a spring or the spring potential energy, we will use the equation 1/2 times k, which is our spring constant, times delta x squared, where delta x is the distance that our spring is moving. And so the unit for our spring constant is newtons per meters. And the difference or the distance that the spring travels has units of meters. But remember, we're going to square this. So this will be meters squared after you do the calculation. And so we'll now take a look at each of the three parts of this week's experiment. And I would encourage you, if you have not done so already, to go through and review and highlight the important parts of the procedure for each part of the experiment. This experiment, probably more so than any of the others that we do, is very important that we follow the steps in the correct order. And so, a special attention to detail on the procedure will be very beneficial to you in preparing for this week's experiment. And so, in part A, we're going to look at a system where an object is experiencing free fall. That is, we're going to drop an object through a pipe, and at the bottom of the pipe, that object will pass through a photogate beam, allowing us to measure the velocity of the object at that time. In part B, we're going to use a spring launcher. That is, we will have a small steel ball in a spring. We'll be able to calculate the spring potential energy, and then we'll be able to measure the velocity of the object, which will allow us to calculate the kinetic energy. And then, using the maximum height that the ball travels, we'll be able to calculate the potential energy due to gravity. Finally, in part C, a part of the experiment that you're going to be more familiar with is, again, we're going to be looking at the object of a car that is moving on an inclined track. And so we've used these tracks the last 2 weeks. In each of the weeks, we've started the car kind of at the top side of the ramp, and we've watched it fall down the ramp. Or last week, we looked at what happened whenever a force was acting on the car. In this week's experiment, we're going to begin with a car at the bottom of the track, and we're going to allow the spring of the car to propel it up the track. We will measure the kinetic energy of the car on its way up the track. We will measure the potential energy of the car when it reaches its highest point on the track. And then we will measure the kinetic energy of the car on its way down the track. Let's take a look at the three data tables. So in part 1, when we are looking at our object in free fall, here we have a kind of purple colored cylinder, and we're going to take some measurements. We're going to measure the height of the cylinder at the beginning. This height is going to be our h, our height of the drop, as highlighted here in our data table. Let me switch colors here. So here is our height. Try that again. All right, so here's our height. We'll measure the height. This will allow us to calculate the potential energy. Remember, the potential energy is the mass times the acceleration due to gravity times the height. And so if we have the mass of our cylinder, m, and we have the height of our cylinder, h, and we know acceleration due to gravity, g, we can calculate the potential energy of the cylinder. Finally, we will use our timer reading of our cylinder at the bottom, which will be measured by the photogate, t, to calculate our velocity, where the velocity is going to be equal to the length of the cylinder divided by the time. And so obviously we'll have to use a length in units of meters and divide that by seconds to get the velocity at the bottom. Once we have the velocity, we can calculate our kinetic energy because it is equal to 1/2 times the mass remains the same, times the velocity squared. So in part A, we'll be taking two energies, the potential energy at the top and the kinetic energy at the bottom, and we'll be comparing these energies to one another. In part 2, the spring launcher, we have a little bit of a hasty diagram here. We have our spring at the bottom, and this spring will have a constant K, which will be written on the spring, and that constant has a unit of newtons per meter. And so, to calculate the energy of the spring, it's equal to 1/2 times our spring constant K times delta x squared, where delta x is simply going to be the difference between our initial plunger position, x sub I, and our final plunger position, x sub f. And so taking the difference between these two will allow us to calculate our delta x in units of meters. This will be used to calculate our potential energy of the spring. Next, we will measure the time it takes for the steel ball to pass through the photogate at the bottom. In doing so, this will allow us to calculate our kinetic energy, where again, our kinetic energy is equal to 1/2 times the mass times the velocity squared. We will determine the velocity by taking the diameter of our sphere, indicated here. You'll measure that in millimeters and convert it to meters. And you'll divide that by the time of the photogate, given in seconds. So again, our velocity will have units of meters per second. And when we do this, we'll be able to calculate our kinetic energy, 1/2 mv squared. Finally, as the steel ball travels upwards, we will measure the ball at its highest point. And this will give us a height. Now, this red rectangle over here is our ruler. And we will use this ruler to determine the maximum height of the object. So again, our potential energy is going to be equal to the mass of the steel ball times the acceleration due to gravity times the maximum height that the ball travels. So in this part 2, or part B, excuse me, table 2, we have the potential energy of our spring, we have the kinetic energy of the steel ball as it passes through the photogate, and we have the potential energy of the steel ball at the top. Finally, in our final portion of the experiment, table 3, we will again be using a car. We will record the mass of the car, and we will measure the length of the flag on top of the car here. We will use some very basic trigonometry using the overall length of the track and the overall height of the track. This will allow us to determine the height, the vertical height of the car at its highest point. We'll talk more about this in lab tomorrow. However, we will measure the kinetic energy of the car as it moves up the ramp by measuring the amount of time it takes for the flag to travel through the photogate on its way up. The car, after it moves through the photogate, will reach its highest point, and we will measure this highest point as the distance that the car travels to. Then the car will fall back down or come back down the ramp, and we will need to reset the photogate timer at this point so that we can get a reading of the flag, and that is our t sub down. And so we will end up with two velocities. We'll have our velocity of the vehicle as it moves up, which is the length of the flag divided by the time it takes for the car to move upwards through the photogate. And then our velocity on the way down, which again will be the length of the flag, which should be unchanged, divided by the time it takes for the flag to travel through the photogate on the way down the ramp. We will then be able to calculate the kinetic energy of the car on its way up, where again, this is going to be equal to 1/2 times its mass times its velocity squared. On the way down, again, it'll be equal to 1/2 times the mass times the velocity squared. And our potential energy will be equal to m times g times h. And our overall h determination, again, we'll talk about how this value is going to be determined tomorrow in class. Just know that this h right here is going to be the h that is used in calculating your overall potential energy. This concludes our video for experiment number 4. I hope that this video is helpful, and if you have any questions, please do not hesitate to reach out to your lab instructor. Thank you all, and have a great day.